Here we are with 12.5 related rates. We're going to take a look at solving these types of problems. So there's not too much to talk about except for this one slide here, which sort of gives us step by step how to go through it. Excuse me. So when we come to solving related rate problems, we first need to list the related changing quantities. So what are we talking about? We list them out, what the variables are. We're going to restate the problem in terms of rates of change. And remember, this is where the derivative comes in. Rates of change are, well, they come from a derivative. We're going to look at a relationship. Maybe we'll draw a diagram to see what quantities are changing. We're going to need to find some sort of equation which relates the rates and the changing variables. And what we will be using primarily through all of this is implicit derivative. So we've got that section to review a little bit earlier on. So this is when we're actually sort of mostly an application of implicit derivatives. Once we have that set up, we move on to the solution. We substitute in all the things we know about the implicit derivative. We'll be able to put in variables. Everything except for one thing will be left unknown, and that one thing that is unknown, that's what's requested in the question. That's what we solve for. So let's take a look at a few examples. Some of these you're going to have to remember formulas from geometry, various other areas, distance possibly. So let's take a look at an example here. So again, the question numbers don't match up exactly with the study guide. But the questions are the same. So the complete study guide will have different numbering. So the radius of a circle, but this is the first one in 12.5. Okay. The radius of a circle puddle is growing, a circular puddle is growing at a rate of 15 centimeters per second. So that's a rate, that's a derivative. Okay. We're asked how fast is the area growing in the instant when the radius is 30 centimeters. So actually, let's go ahead and address that one. And then we've got the next one. Okay, so we've got a circular puddle dealing with a radius, and we're wanting to look at, by we get down here, we're looking at area. So what is an equation that relates area and radius? Area is equal to pi r squared, radius squared. Okay. And we're given information about a particular instant in time when the radius is 30 centimeters. So the way we go about this is we want to, now notice this area equals pi r squared has nothing to do with time. There is no time in this. Where the time comes in is we are going to take a derivative, because notice time is definitely involved here. Time is a sort of an invisible variable here. So we're going to take the derivative of this formula, this equation, with respect to time. So the derivative of A, area, is 1 dA dt. So A itself, if you took its derivative, would just be 1, but we have to list what, remember from implicit derivative of A with respect to t. On the right-hand side, we're going to take the derivative of r, so that the 2 comes down in front. So we get 2 times pi times r, 2 minus 1 is 1. And then what did we do? We took the derivative of r with respect to t, dr dt. So this is the formula we're going to be using. It's got the rate of change of the area, the rate of change of the radius, and also the radius here. So for the problem we've got, we're given for the A part, we're given the radius, r equals 30 centimeters. And at the outset, we were given the rate, the radius of circumpolar, the radius is growing at this rate. So this is dr dt. Okay, so dr dt equals 15. We substitute that in. We're going to substitute 30 in for r. So that gives us that dA dt equals 2 pi times 30. Dr dt is 15. And now notice all we have to do is the arithmetic. You could, if you want, 2 times 15 is 30. 30 times 30 is going to be 900 pi. So dA dt is 900 pi. And I'm not sure whether they want that as a decimal or not. Sometimes if they want the exact answer, that's what we're left with. Otherwise, it's 900 times pi equals 2,827. Was it 43? It was 0.43. If they want 2 decimal places, again, they'll just tell us what they want. So either this is an approximate answer, this here is the exact answer. How fast is the area growing when the area is 81 square centimeters? For this one, you have to think a little bit through it. We can't just start with the derivative formula because there's no place to plug in the area. We need the radius. So how are we going to find the radius? We use the first formula before we took the derivative to find r. Okay, so we start with a area equals pi r squared. We put 81 in for the area because that's what we're starting with. Now we solve for r. So we divide both sides by pi. And we get that r squared is equal to 81 over pi. Take the square root of both sides, which gives us, now it gives us a plus or minus, but a negative radius really doesn't make any sense. Square root of 81 is 9. Square root of pi is the square root of pi. And we can go ahead and figure this out, and we will probably need to be able to plug in that r. So we're going to have 9 divided by pi, and to do a square root, I'm going to raise pi to the 0.5 power. See if that worked out right. Let me double check this. So if I did 81 divided by pi, I do that first, and then I'm going to take the square root and then raise that to the 0.5 power. I get 5.08. Okay, so that's r. Now it's basically, we're back to doing what we did on the last problem. We take our derivative, because this is what we're looking for, dA dt equals 2 pi r dr dt. We have the r right here, 5.08. The r dt is still 15, so that's going to go in here, and then we'll be able to find the ADT. The RDT is 15. So we just go ahead and multiply all that out. Suppose we could have, well, could have left the square root of pi, but so we'll do 2 times 5.08 times 15. So you could write it as 100 and what was that, 152.4 pi, but it's not really exact anyway because we've rounded here. So let's go ahead and multiply that times pi. 478.78. 478.78. Okay. And that, since it's area, the rate of change of area, it's going to be square centimeters or centimeters squared per second, right? It's in all, and the units are second per second. Okay. So the first answer was 2827. 2827, they round it to one decimal or to no decimal places. And then the last one, 479, they rounded to nearest whole number. So that's fine. We had the correct answer, and if they would have told us exactly what they wanted rounded, we would be right on track. Okay, so that's that one. 7, a rather flimsy spherical balloon, so we're going to need the area of a sphere, is designed to pop up at the instant its radius has reached 6 inches, or 6 centimeters radius. Assuming the balloon is filled with helium at a rate of 13 cubic centimeters per second, so this is a change in volume, calculate how fast the radius is growing at the instant it pops. It's going to pop when it reaches 6 centimeters. Okay, and this is a rate, so this is a derivative. It's a rate of change of the volume, so this is our dv dt. We're looking for the changing of the radius, which is dr dt. So how fast? That's the question. We want to know this rate. So we have to relate it to a volume. Let me see if I can remember this correctly. The volume of a sphere, I think it's 4/3 pi r cubed. I know it's cubic because it's volume. And from my memory, if it serves me right, a sphere is going to be 4/3 pi r cubed. Let's take a peek down below. Actually, what would you do? These are the types of things. Yeah, 4/3 pi r cubed. Hopefully the question would give you that formula, because that's kind of one I wouldn't expect you to know right off the top, but here we are, we're practicing, right? So again, we've got the volume related to the radius. We take implicit derivative of both sides, so the derivative of volume is 1, but we've taken the derivative of a volume with respect to time, so we have to put that sort of marker in there. 4/3 is a constant, pi is a constant, so those stay there. They're constant multipliers. Take the derivative of r, so the 3 comes down and multiplies. We're going to get to cancel these 3 out, but subtract 1 from the exponent, so now you have r squared. And using implicit derivative rules, we took the derivative of r with respect to t. That t is that invisible variable that is involved here because we have a dynamic situation. Okay, so what we can come here is the 3's will cancel. So dv dt is equal to 4 pi r squared dr dt. Now, let's come back here. What is constant in this case is the change of volume, because there's a rate that the air is being put in there. If you know anything about helium, it's a gas that doesn't compress much, so when it goes in, it should be giving you that same volume change. So we've got the dV dt here. So this is going to be 13 on this side. We've got 4 pi, and we're told that it will pop when it reaches 6 centimeters, and that's the instant we want to know how fast was it changing. Of course, I don't know why, because it's not going to change anymore, right? But we're going to plug in the 6 here. Maybe it would answer the question of, how fast was it going, and so maybe that tells us how fast the balloon shreds would fly off and whether it'd be dangerous or not. Okay, so this is dr dt. How fast is the radius changing? Okay, so again, we just do the math. Let's just go up here to keep it all in nice little flag. So we get 13. 6 squared is 36. So 4 times 36 pi. Do it that way. Dr dt. Let's go ahead. 4 times 36 is 4 times 6 is 24. 4 times 3 is 12. With the carried 2, that's 144 pi dr dt. So divide both sides by 144 pi. So it gives us dr dt 13 divided by 144 pi. We want to make sure we got this with the order of operations. I'm going to try that again. 13 divided by, I'm going to go parentheses, 144. Let's try this again. 13 divided by parentheses, 144 times pi, close the parentheses, that makes sense, and then equals 13 divided by that larger number, 0.0287. And it doesn't say the rate or how many decimal places, but that would be centimeters per second. Again, we've got to look at the rates that they're giving us here. So this is centimeters per second. They might round it to 0.03. Let's see, what did they do? Yeah, 0.03. Let's bring that up a little bit. Okay, so that was 7. Had to pull that equation out there, but I think, if they gave us this problem, that was probably something they wanted us to know. See this one, they don't really tell us too much, but they give us the average cost function in this case. So for 8, the average cost for the weekly manufacture of retro portable CD players given by this function here, where X is the number of CD players manufactured that week. Weekly production is currently 4,000 players. So that's an X value, right? That's what they told us. Weekly production, X is the number made in a week, and is increasing at a rate. So here's a derivative of 400 players per week. That's the derivative, the dx dt, right? Let's go ahead and label that. What is happening to the average cost? So we've got x here, we've got our cost. What we want to do is take the implicit derivative of both sides. So let's go ahead and just kind of list it. So the derivative of the average cost is, if we want, it's dc of x dt. So it's the derivative. You could use the prime notation here, but that's that part. This part is the derivative of x. So when we take the derivative of x, the negative 1 comes down. So that's minus 120,000, because negative 1 times 120,000. X, we subtract 1 from the exponent. That gives us x to the minus 2. This gives us a dx dt, because we took the derivative of x with respect to time. 20 is a constant, so when you take its derivative, it's 0, so that part's just gone. And then this part here, when we take its derivative, x to the first power, is going to be just simply 0.0004 dx dt. dx dt. So now what we are looking for is what is the change, the rate of change of the average cost. What is happening to the average cost? This is going to be the rate of the average cost. So we just need to plug things in. We need to plug x equals 4,000, and we need to plug in dx dt equals 400. Okay, so we'll do that. So I'm going to go back to the other notation that the average cost function, the derivative of the average cost function, is going to be minus 120,000. This is x is 4,000, to the minus 2, times dx dt, which is 400, plus 0.0004 times 400. And we just need to plug that in a calculator. It's all arithmetic at this point. Looks like I got it right. Okay. So let's pull up a calculator. Try to get the order of operations. So I've got 120,000. And that's a negative number, times 4,000. Use this x to the y raised to the 2 negative. There's our exponent there. We get that number, times should still be a negative number, I would think. Okay, let's see if we times 400. Okay, now it's done it. So now it's shown here. It's us negative 3. The second part here, 4 times 4 is 16. This will go back up. A 0.16 is what I think it's going to be, but why not use the calculator while we've got it? 0.0004 times 400. Yeah, 0.16. Good job, little crow. So negative and a plus, so we're going to subtract. Looks like our derivative, our average cost is decreasing by what? That's 2.84. Sometimes I get that, negative 2.84. So we could say it is decreasing at a rate of $2.84 per player per week. Not bad. Our costs are going down. Let's see. 284. That's what it was. Minus. So, yeah, DCDT. Okay. I'm not sure what all this is. This is DCDX, DXDT. I just go straight forward with the implicit derivative, the way we've been doing. It worked. Okay, so that's 12.5. I'll record this down and put it into Canvas, and keep up your good progress on studying, and you'll be well prepared for test 2. Thank you.